All right, this is going to be part 2 of the solutions for the rotational dynamics assignment that was posted. And so let me do a screen share here. Excuse me. Let me do a screen share here. Okay. And I'm going to go over the next couple problems on our assignment, and then I'm going to leave the last one for another video because that one's a little more involved and it'll be a good one to do by itself. All right, so number 6 says, sometimes even with a winch, one cannot loosen a nut that is frozen tightly to a bolt. It is often possible to loosen the nut by slipping a long pipe over the wrench handle and turning the nut. Explain why this trick works. Well, it works for the same reason that if you've ever changed a tire, the tire iron that you use has those long arms to it. And the reason it has those long arms to it, let me actually do a stop share here. The reason it has those long arms to it is because if we want to get something to rotate, our equation that we want to think about is torque, tau, is equal to the force times the radius. Meaning, if we can increase that radius, keep in mind the radius means the distance between the pivot point or the axis of rotation and the area where you're applying the force. So if we can increase the length of that wrench, we can get a greater torque out of it given the same force. So the longer that arm or that wrench is, the greater amount of torque that you can get out of it. All right, so what is the next question? Next one says, explain how it is possible for a large force to produce only a small or even zero torque, and then explain the opposite. We'll think about this equation again. If you're trying to, well, let's say you're applying a very large force, but you're applying it really close to that pivot point. So for instance, you're trying to open up a door, but you're pushing on that door right next to the hinges. Okay, it's really hard to get a door to open if you're pushing on it right next to the hinge. And the reason for that is because your radius then is very small. So even with a great force, you're still only getting a little bit of torque out of it. Well, similarly, if you apply a small force, but it's far away from that hinge point, so for instance, it's on the other side of the door, then you only have to apply a small force to get that same amount of torque out of it. And so it's much easier to open a door when you push on it on the opposite side of where the hinges are located. So it's really for the same reason. All right, number 8. Number 8 says we have a square with a side of 0.4 meters mounted so that it can rotate about an axis that passes through the center of the square, which is kind of weird. And the axis is perpendicular to the plane of the square. Okay, perpendicular to the plane of the square, and it wants to rotate about its center. Okay, and we have a force of 15 newtons. And so what we have is a square like this, and we're trying to get it to rotate about its center. Well, if the side is a length of 0.4 meters, then we know that it's 0.2 meters from the center to one side. And it's a square, so therefore this is 0.2 meters too. Now you might be tempted to say, okay, well, tau is equal to the force times the radius. Well, the radius would be the distance between that pivot point or that axis of rotation and where you're applying the force. So I'm going to apply the force, you might think, right here. And that will give you a large torque. But there's a farther distance away, because keep in mind what the problem actually says is the problem says, what is the maximum torque that such a force could produce? Well, the maximum amount of torque wouldn't be from the center to the side, it would be from the center to the corner. That's the greatest radius right there. And so if you want to apply the greatest amount of torque, you would have to apply it at a distance that's farthest away from the center. That corresponds to this right here, so that would actually be our radius. And so in order to find that radius, you just do a little Pythagorean theorem. So that's 0.2 squared plus 0.2 squared, and then you take the square root of all that. You should get 0.283 meters. And then you just plug this 0.283 meters into our torque equation. So that's 15 times 0.283. What do we get when we do 0.15, or I'm sorry, 15 times 0.283, 15 times. So you should get about 4.24 or 4.25. And so then our torque is 4.24. Where the units for it, the units are just newtons times meters. It's the unit of force, which is a newton, times the unit of length, which is a meter. Okay, let's try to fit in one more problem. Do my screen share, actually. Okay, there it is. All right, so number 9. Number 9 says, what is the net torque about the axle? And so if you look at this problem, this little dot right here represents the axle. And so if we're, well, first off, this 50 newtons right here that's going straight towards the axle, that has a distance of 0 from the pivot point. And so that's not going to make it rotate at all. But this 50 newtons on this side over here will make it rotate. And so, well, what distance is it from that axis? Well, it's just 0.1 meters. And so this is pretty simple. Then you just multiply the amount of force, which is 50 newtons, times the distance, which is 0.1 meters. And so let me just, and then there's also another way to think about this too. No, I don't want to say that. Okay, never mind. So in other words, the torque for this problem is just going to be equal to the force times the distance from it. And so that's just 50 times 0.1. So we get 5 meters. Pretty straightforward. All right, so I'm going to stop right here, and then I'm going to make another video on the last problem.